We previously learned about Hooke's law, but that was only applied in 2D. Now we are going to apply it in 3D. What we understand is that expansion and compression can occur in 3 dimensions. We're going to use Poisson's ratio, which if you remember is the ratio between expansion in one direction over the other. Then we will use the 2-dimension Hooke's law, but we will combine the stresses in the different directions, x, y, and z. And this is 3D's Hooke's law. I used B and C here just because it will be the same equation, but will depend on what you want to find. Strain in the x, y, or z directions. Some important notes to make about 3D Hooke's law are: if the material is restrained, meaning that it can't grow or shrink, it will not have strain in that direction. An example is a wall. It can't grow past the wall. If a material is unrestrained, it cannot feel stress in that direction. If it is open in a direction and will never touch a wall, then there will be no stress in that direction. And finally, if the material is being loaded, it will be strained and stressed. If there is a load applied to the material in a specific direction, there will be both stress and strain present. Here is our example problem. We want to find out how much of the material will expand in the z direction. The z direction is coming out of the page. We are going to solve this symbolically. I designed this at a different orientation to help understand how the load will be applied. Because of the forces, it will shrink in the y direction. But because of the wall, it can't move in the x direction. That means that the material must go in the z direction. First, we will write our equations. Then we will state our known information. Like we know that there will be no expansion in the x direction. We know that sigma y is sigma naught in compression, and we know that there will be no stress in the z direction because it can expand freely. Finally, we will plug in our known values into those above equations. Now that we know the derived equations, we can start solving for variables and substituting into the other equations. First, we can solve for sigma x by getting rid of all the zeros in the first equation and solving for sigma x in terms of nu and sigma naught. Then we can plug into epsilon z equation all the known variables, and that's what we're solving for. Then we will notice that there are only known variables in that equation, and we will begin to solve for the expansion in the z direction in terms of Poisson's ratio, elasticity, and the stress applied in the y direction. And we get this.